So this is solar cell is a simply already we have discussed yesterday also simply PN junction diode. Okay, PN junction diode, it will convert optical energy into electrical energy. Optical energy into electrical, or you can say sunlight or light. Optical means light energy or light. Just you can write simply light also into electrical energy or electricity or current. Okay, by using photovoltaic effect. Okay, that is we have discussed already. Photovoltaic effect. Okay, that is Okay, photovoltaic effect means even if you shine some light on a material, electrons will be generated. Okay, electrons holes will be generated, but these electron holes, they will not leave the material, they will stay within the material only, but these electrons are free to move within the material. That is the photovoltaic effect. Okay, so here we will connect the PN junction condition. Okay, condition we will apply. Okay, this is the simple definition of solar cell. Okay, the working principle is already we have discussed yesterday, but still we will go through once quickly. Working principle. Okay, first thing is we have three steps. We have mainly first one, we have to we have to generate electron holes. Okay, what is generation of electrons and holes? Okay, by some light or sunlight or normal light, any light. Okay, generally for solar panel utilize the sunlight. Okay, but here we are writing light. Okay, so artificial also we can create sunlight. AM 1.5 condition. Okay, air mass 1.5 condition. This is the sunlight, it is equal to the, this light intensity is equal to the sunlight intensity, that is 100 watt per meter square. 100 watt per meter square or 1000 milliwatt per meter square. This is the irradiance we will get the from sunlight. Okay, this is 100 watt per meter square. Okay, first we will generate electron holes. After that we have to separate these electron holes. Okay, separation of these whatever generated electron holes we have to separate. Otherwise, if we not separate this one, this will again recombine, it will not produce any current. There is no use of generating electron holes. That's why we have to, after generating electron holes, you have to, next job is to immediately you have to separate this one. How you will separate this one? Using internal electric field. Okay, internal electric field, you have to separate these electron and holes. Third thing is collection of charge carriers. After separating, we have to collect these electron and holes. Okay, I will collect by metal contacts. Okay, by metal contacts you will collect it. Okay, metal contacts. Okay, first step is to generation of electron holes by shining some light. Second step is after generating electron holes, we have to separate immediately by using internal electric field. Okay, final step is we have to collect. After separation of this, electron will go one direction and holes will go opposite to the electrons. Okay, because these are opposite polarity. Okay, so electrons, after that we have to collect these electron hand holes using metal contacts. Okay, this is the simple definition and working principle of solar cell. Okay, up to now, is it clear to you? Anyone having doubt up to here? Is it clear, you guys? Is there
Yes,
any
sir.
doubt here up to now? Okay, now we'll go to next using band bending and this energy diagrams. We will understand how this will work. Okay, so first we will see P. This is simple PN junction diode. Okay, P type is, in P type majority carriers are holes and N type majority carriers are electrons. Okay, that we will draw again. Okay, that we have discussed this PN junction already, but again we will go through this one. Okay, that time only I told you, once you understand this PN junction, it is very easy to understand every topic in a third unit. Okay, left side is P type semiconductor and right side is N type semiconductor. Okay, that is we are taking as a we are first bringing the, we are bringing two semiconductors and forming a junction. Okay, to fabrication of these techniques we have different techniques. Okay, that we will see, that is chemical vapor or using gases, and this thing gases are a solution, wafer, you can create wafer, and also this we can do it. Okay, but here just for schematically we are bringing together. Okay. So generally silicon is the best solar cell material. Okay, silicon is made by earth only. Okay, this is will come from silicon oxide. Okay, this is just a silicon SiO. Okay, this is also simple sand only. Okay, from the sand we are purifying the silicon. Okay, after that we will create wafers like a circular or square type wafers. They will arrange in a one by one. Okay, after making solar cells using wafer we will arrange in a systematically. Okay, then this is a we are calling a module. Okay, systematic arrangement of solar cells in a row, that is we are calling module. That is we are seeing in a homes or in market we are showing this kind of things we are seeing only. We are seeing modules only. Okay, we are not seeing solar cells particularly. These are arranged in a systematic manner. Okay, that is a different and semiconductor. All of you know holes are the majority carriers in p-type semiconductor, right? Holes are the majority carriers, that you know. So similarly in n-type semiconductor. Okay, that is also you know we are discussing many classes. Okay, this is the hole electrons. Okay, now because of charge gradient, electrons will diffuse towards the p side, and similarly holes will diffuse towards the n side. While diffusing, electron diffusion means electron leaving n-type semiconductor. That means it leaves a positive donor atom here. Okay, positive donor atom. If electron leaving this area near the interface, okay, they leave a positive charge density. Similarly, when holes leaves this p region, they leave a negative acceptor density. Okay, when hole leave to inside, they leave a negative acceptor density. This is what we are calling space charge region or depletion region. Okay, space charge region or depletion region we are calling. Okay, after the this is up to equilibrium condition. This diffusion continues. Okay, diffusion of electrons and diffusion of holes will transport until equilibrium condition. Once the equal number of holes and equal number of electrons charge is balanced both sides, there is no flow of electrons and holes. Okay, after that we are connecting reverse bias condition. Our device we are connecting reverse bias condition because solar cell will work under reverse bias. Okay, that is useful current will get under reverse bias only. So p-type semiconductor connecting to negative terminal, right? That is reverse bias condition. And positive terminal is connecting to n-type semiconductor. Okay. Because of this one, what is happening? The electrons are attracting towards the potential barrier, a potential or battery, and holes also attracting towards the potential of negative potential. Okay, because of this one there is a increase in depletion width. The depletion width will be increased. Okay, here the depletion width will increase, that is you know. Okay, once you connect the semiconductor or p-n junction the negative terminal. Because of this one the depletion width will increase. Okay, if depletion width is increasing means here we are charge density in the depletion region is increasing. Okay, charge density in the depletion region is increasing. That means earlier this is the electric field. Now the electric field is this much because more charge density is there. Already we have discussed yesterday. E is equal to capital E electric field nd by epsilon naught into x. So here electric field is always proportional to the charge density or acceptor or donor charge density. That's why if donor charge density or acceptor charge density increasing in reverse bias condition in the depletion region, so because of this increased charge density in the depletion region, the electric field also increase. Okay, this is condition for reverse bias condition. Okay, so in reverse bias condition what is happening? So once this depletion region is forming, there is a potential barrier. Okay, because of this potential barrier, electron they will not overcome this barrier. And also here one throughout the means borders of the screen we will see one red mark, that means sharing. Okay, so that's why I did not see. Okay, okay, anyway, thank you for informing me. Okay, so here why is it clear my voice also? Voice is it clear,
Yes,
my voice?
yes, sir.
Okay, thank you. Okay, thank you. So here electric field is proportional to the charge density. Either this donor acceptor or acceptor. Okay, donor density or acceptor density. Okay, so because of this increased electric field, there is a development of potential barrier or some height or some barrier. Okay, so electrons, remaining electrons in n-type semiconductor, they don't have that much energy to cross that barrier. Similarly, holes also doesn't have that much energy to cross the barrier. Okay, now here we have sufficient electric field, but the direction is positive to negative, n-type to p-type semiconductor. So we know n-type we have minority carriers or holes. Only few minority carrier holes will be there in n-type semiconductor. And similarly, in n-type p-type semiconductor, electrons are the very minority carriers. Okay, because minority carrier means density of electrons are lesser, very less in p-type semiconductor. And in n-type semiconductor, if you take n-type semiconductor, density of electrons is much greater than the holes. And if you take p-type semiconductor, hole density is much greater than electron density. So that's why density, because of the density, electrons are the minority carrier in p-type semiconductor and holes are the minority carrier in n-type semiconductor. Okay. So because of this internal electric field, whatever minority carriers, that will drift from N to P. So here, because of this internal electric field, holes will drift towards the P side. Okay, holes will drift. Drift process will dominate. Similarly, electrons in p-type semiconductor also drift towards the n-type semiconductor. So in reverse bias condition, you remember always drift drift transport process is the main dominant process. Okay, diffusion is mainly due to charge gradient only. Okay, drift means you are using electric field energy or electric field to send one type of charge carrier one direction and others in opposite direction. Okay, drift means charge carriers are going one place to other place by the external force, that is here electric field. Okay, here drift process is main dominant process. Now we will see, this is simple PN junction diode. Now we will apply. So please mute, man. Okay, now this is simple PN junction under reverse bias. So now we will shine the light here. Okay, we will shine the light. Okay, throughout the semiconductor we will shine the light. Okay, we are shining light in depletion region and n type and p type. So in n type and p type bulk region, electron holes will be generated, but this electron hole will be recombined because there is no electric field to separate these electron holes. And here also in p type, also in the bulk region, there is no electric field. Even after shining light, there is a generation of electron holes, but these electron holes will be recombined because there is no electric field to separate that electrons and holes. Now in the depletion region also, electron hole will be generated in the depletion region or space charge region. So here electric field is strong, electric field is present in the depletion region. Because of this electric field, whatever generated electron holes are the minority carrier. This is going to, holes are going towards the p-type semiconductor and electrons going towards the n-type semiconductor. So electrons only going to n-type, that means in the n-type semiconductor electron density is increasing, and similarly in p-type semiconductor hole density is increasing. Okay, because holes only coming towards p-type and only electrons are coming towards n side. Because of this separation, this electric field is mainly useful to separate electron and holes, and also sweeps the electrons towards n type and holes towards the p type. Okay, that's why there is no recombination losses in the semiconductor. Once this will separate, we will collect electrons and holes separately. Okay, using metal contacts. This is a simple working of the p-n junction diode or solar cell. Okay, simply we will connect the reverse bias and we will shine the light. Using this light, we will generate electron holes, and this electric field, it is present in the depletion region, will sweeps the holes towards p-type semiconductor and electron towards the n-type semiconductor. Okay, because of this one electric field, there is no recombination losses. So our active area is only depletion region. Whatever electron holes generated in the depletion region only causing giving a current in a solar cell. Okay, that is the simple working of the solar cell. Okay, is it clear you guys how this is working solar cell? Do you understand now how the work how the solar cell is working? Anybody, please? If you have doubts, you can raise hand. Otherwise, you say yes or no. Otherwise, I will explain one more time because this is very important question, important topic. Is it clear to you? No? Please respond. Is it clear?
Sir, repeat it.
Okay. Yeah. At least tell me that. Okay. Otherwise, we cannot know whether you are understanding or not. So here I will go through again. Please listen carefully. So we are first what we are doing here. We are taking a p-type semiconductor and n-type semiconductor, right? So when you combine left side, we are taking p-type and right side n-type. So when you bring two semiconductor, there is a junction. We are calling this one p-n junction. Okay. At the middle line, it is a interface. Okay. We know in p-type semiconductor, holes are the majority carrier, right? Holes are the majority. That is, you know. In n-type, electrons are the majority carriers, right? Electrons are the majority. So this is done. Okay. After that, here we are not connecting any biasing condition. So here holes are the minority in n-type and electrons are the minority in p-type. So minority means density of electrons are lesser compared to holes in p-type and density of holes are lesser compared to electrons in n-type semiconductor. Now thing is in n-type electrons are higher density, right? So because of this one electron will diffuse towards the n-type p-type semiconductor. Once this will diffuse, it leaves a positive donor density. That means n-type means what? Here silicon plus some phosphorus. This is third group atom, fourth group atom, and fifth group atom. Fifth group atom. So fifth group atom. So here phosphorus atoms we are calling a donors. That means it will ready to donate electron. P type means here P type semiconductor means silicon. Sorry, just P type semiconductor means silicon will be there and also silicon will be there and also third group elements also there. Okay, just a second. P-type semiconductor means you always remember P-type means not only silicon plus some third group element. Here we are taking boron atom. Okay, this is acceptor atom. Okay, is having negative charge and donor atom always having positive charge. So when electron diffuse from N to P-type semiconductor, it will leave a positive donor, that is plus charge. Okay. Similarly, when holes density is higher, this will diffuse towards the n-type semiconductor. So once this will diffuse, it will leave a negative acceptor density. Okay, negative acceptor, it will leave the acceptor atoms. You remember that. Okay. So this is we are calling a space charge region or depletion region. This is space charge region or depletion region. Because of this plus and negative charge, there is a electric field, internal electric field. Okay, internal electric field. Okay, internal electric field. So this is simple PN junction without connecting any battery or any potential. Okay. Now this will continue until equilibrium position is acquired, or when equal number of electron holes will be there both side, or charge is balanced both side of the junction, there is no flow of electrons. Okay, this is the equilibrium condition. Now our solar cell will work under reverse bias condition. That means reverse bias means, so here what we are doing, negative potential is connecting to positive terminal. Okay, negative potential is connecting to positive terminal of the battery. Just a second. Okay, okay, I will see. Negative potential is connecting to pos negative potential is connecting to positive terminal of the battery, and positive potential is connecting to negative potential of the battery. This is the negative and positive here. Okay, p-type semiconductor is connecting to negative potential and n-type semiconductor is connecting to positive potential. This is the reverse bias. So negative potential attract the these holes towards the potential or battery, and this positive terminal attract these holes towards the battery. Because of this attraction of electrons and holes towards the potential or towards the battery, the depletion width is increasing. The depletion width is increasing. Okay. So here the depletion is width is increased. That means more positive charge density is developed in the interface and more negative charge density is developed in the interface, right? More positive and negative charge density developed in the interface. Now because of this increased charge density, the internal electric field also increase here. Okay, that is E internal electric field. Internal electric field also increasing. This is reverse bias condition what is happening. So because of this internal electric field, only minority carrier holes in n-type semiconductor only drift towards the p-type semiconductor, and also minority carrier electrons here drift towards the n-type semiconductor. This is the drift process will dominate one in reverse bias condition. In reverse bias condition, always you remember drift process will dominate. Drift process means lower concentration to higher concentration. Charge carriers will flow from low concentration to high concentration with the help of some external force. That is the drift process. Okay, lower concentration to higher concentration. Drift means you remember lower concentration to higher concentration, or low density to high density. So low to high it will not flow. That's why we are utilizing the electric field to send these electrons and holes. Using internal electric field, we are drifting the minority carrier electrons from N to P and minority carrier electrons from P to N. Only in reverse bias, drift is the dominant process. Okay. Now this is done. Now our solar cell, for solar cell we are utilizing sunlight. We are shining the sunlight throughout the semiconductor, right? So up to now we have studied only reverse bias condition only. Now we are shining the light throughout the semiconductor. Once this light is shining, because of this photovoltaic effect, electron hole will be generating throughout the semiconductor in the depletion region, in the interface, in the bulk region. But in the bulk region, electron hole will be recombined because there is no internal electric field. But whatever generated electron holes in the interface will drift. There is a electric field here in the depletion region, also electron holes generating, right? But here we have sufficient electric field in the depletion region. Because of this electric field, holes are going towards the p side and electrons going towards the n side. So electric why holes are going towards p side means electric field direction is positive to negative. So hole also having positive charge. So holes are going towards the p side and electrons are going towards the n side. Because of this one, in n-type semiconductor, only electrons are coming. In n-type, electrons are the majority. So electron density is increasing in n-type semiconductor. Similarly, hole density is increasing in p-type semiconductor because of reverse bias condition. Okay. Now thing is, we have separated these electron holes using internal electric field. Now thing is to we have to use we have to use the metal contacts to collect these charge carriers. We have to use the, up to now, we shine the light, we have generated electron holes, and using internal electric field, especially using internal electric field, we have separated these electron holes. Only holes going p side, only electron going towards the n side. I'm explaining 2-3 times because of this delay. So this is left side is p type semiconductor and right side is n type semiconductor. Can you see the diagram? Can you see band bending diagram? Okay. So this is EC and EV and EF. Fermi level, conduction band edge and valence band edge. Right side also this is EC, EF and EV. Okay, this is the thing. P and N type semiconductor we have connected. So here we are applying reverse bias condition. Okay, reverse bias condition. Okay, that is already we have discussed the same thing. So this is here we know free electrons are there in N type semiconductor and free holes are there in P type semiconductor. Okay, that is we are drawing. So this is the once junction is forming. This is the depletion region. Okay, this is the depletion region. Okay, here the potential barrier height is this much. Okay, this is the potential barrier height. This is VBI, built-in potential or potential barrier. So electrons see this much height to the electrons from n-type semiconductor after depletion region is forming. Electron see high potential barrier height. Okay, so this they want to, if they want to flow to p type semiconductor, they have to overcome this barrier, but they don't have that much energy, so they will not go to the p side. Electrons will not go to the p side. And similarly, holes also see high potential barrier. They will also not go to the end side. Okay. Because of this one, there is no recombination losses. And here internal electric field also, you can write plus to minus. Okay. Now we are shining light here. Okay. We are shining light here. Because of this shining light here, we are creating electron holes in the depletion region. Okay, we are creating electron holes in the depletion region. So internal field is direction is always plus to minus. Because of this plus to minus, only holes going towards the p side and only electrons going towards the n side. So here only electrons going to p side means there is no recombination. All density is increasing here. Similarly, only electrons are coming towards n side. So electron density is increasing, right? So because of this separation, first you used the light, and using light we have generated electron holes in the depletion region and throughout the semiconductor. But bulk region generated electron holes are recombined. There is no electric field that will recombine. So whatever generated electron holes in the depletion region will be useful for current in a solar cell. Okay. So using electric field, we are separating these electron holes. That is second step is done. Third step, just before I explain, using metal contacts we are collecting this thing. Okay, this is the simple band bending diagram of a solar cell. Okay, here because of this reverse bias, okay, reverse bias, drift process is dominant in the solar cell. Drift process is the dominant in the solar cell. Because of this drift only, we are getting current in a solar cell. If you suppose if you apply forward bias voltage here, let's consider here. If you apply forward bias voltage, what is happen? The electric field reduce and holes will come towards the this side, and here electrons will diffuse, right? So electron will diffuse towards the p side and holes will diffuse towards the n side. That means electron hole will be recombined in forward bias condition. That is no more useful for producing the current in a solar cell, right? That's why we always connect in the reverse bias. We are reducing the recombination losses by connecting reverse bias condition. If you apply forward bias to this PN junction, electron hole will be recombined. In this forward bias, diffusion process will dominate. That's why electron hole will be recombined. Once this recombining means there is no use for producing the current. We cannot able to produce current. That's why solar cell always connecting in a reverse bias condition. Okay, this is the simple uh, for reverse bias and solar cell working condition. Is this clear to you guys? Please tell me your response. Otherwise, I don't know. Again, I will go through again. Please tell me, is it clear? You got the how this solar cell is working? Could you follow the what I am explaining? Could you follow it? Please respond. Yes, please. Any doubt? Are you following or are you not following? Or any doubt? Please tell me. Otherwise, no. Just explaining. If it is not useful for you, it is no meaning. Okay. Is it clear up to now? What I explained?
Clear, sir.
Okay. So okay, no problem. If you have, please go through once I after explaining. Please, whenever you get time, just 5 minutes you go through the topic. Then your concept will be clear. Otherwise, little bit confusion may be there because we are discussing, but you somewhere you may not follow. Okay, so please go through at least 5 minutes daily. At least 5 minutes is more than sufficient if you listen classes. That is I am guaranteed. Okay. So this is working now. We'll go to the IV characteristics. Okay, that is also very important because IV measurements is the give the how much solar energy is utilizing, and from that solar energy how much current we are getting from the solar cell. That will explain. Okay, measuring IV characteristics only we can know solar cell working properly or not. Is it converting sunlight into electricity properly or not, we can know. Otherwise we don't know whether it is converting or not, how much it is converting. So that is why we have to always measure the IV characteristics. Okay, so we will see circuit diagram. First we will have a this is also you have experiment, but because now we cannot do this one. Okay, here we have solar cell. Okay, here we will shine the light here. Okay, here we will connect the ammeter. Okay, this is ammeter. Okay, and here we have a series resistor. Okay, series resistor or as I am writing. Here we have a shunt resistor. Okay, shunt resistance or sh. And here, okay, uh, voltage V output voltage here, and load resistance also we have load voltage and load resistor we have, we will connect here. Okay, this is a simple circuit diagram. This is universal solar cell circuit diagram. Using this one we can estimate how much current once you shine light here, how much current is generating from the solar cell, and how much voltage is dropping across the solar cell we can measure. From there we can estimate the how much efficiency we are getting, how much sunlight is converting into electricity we can see it. This is the simple circuit diagram. Here series resistance, shunt resistance is just these are we are not connecting here. Series resistance means these layers, suppose we have a N layer and P layer. These layers are not perfectly conductors, these are semiconductors. So these semiconductor have some resistance. This semiconductor have some resistance. This is add up as a series resistance. And also suppose electrons